So a gas can do work. Let's consider an example when a gas is expanding and it pushes on the piston, and by pushing on the piston it displaces it a certain distance, and that does work. So initially we have the force of gas on the left and the external force on the right, and they're balanced. Let's consider if the force on the left is greater than the force on the right, and it pushes the piston to the right. By displacing it, we will do work on the piston. So we're going to consider an example where our pressure is constant. Our volume is changing, but our pressure is constant. And pressure constant is an isobaric process. So let's think about how we can come up with what equation we can use for the work done by a gas. So we start with our basic work equation. Work is force times distance, and we're going to know that the displacement is in the same direction as the force, so we can ignore that cosine theta on the end. So work is the force of the gas times the distance it displaces. Well, we can replace the force of the gas with the pressure of the gas times the area, because pressure is force over area, so force is equal to pressure times area. And the displacement we'll just say is the final position minus the initial position. Well, if we write this out, you can see that we're going to end up with the area of the piston times the displacement, which is going to give us the volume. The final volume minus the initial volume, both times the pressure, and we said it was isobaric, so the pressure is constant. So the final equation that we get that you need to learn is that the work done by a gas is the pressure times the change in volume. So VF minus VI. You can look at it on a pressure volume or PV diagram, and you can see that if pressure is on the y-axis and volume is on the x-axis, the area under a graph on a PV diagram is the work that is done, because it's the delta V. So in general, the work done by a gas is the area between VI and VF, the area underneath the graph. So just a couple of notes to remember about when we use this kind of work. The work done by a gas is P delta V. This equation right here is only true, we talked about an isobaric process, so only when the pressure is constant. If the pressure changes, the work is going to be different. But when we look at the area under a graph, that is true for all ideal gas processes, so not just isobaric ones. So the general rule is you can do the area under the graph. If you know the pressure is constant, you can use this equation. Since the volume is going to have to change for both this equation and for the area under the graph for work to be done, that's a general rule. Volume must change for the gas to do work. And in terms of our units, we want our pressure to be in pascals, which is a Newton per meter squared, and our volume should be in meters cubed. Now, the work done by our gas is going to be positive if the piston is expanding or if the volume change is greater than 0. But we're going to have to consider this positive work within the whole system. When we put the work done by the gas into the whole system, the work is actually going to exit the system into the environment. So our work done by the gas has to become a negative work once we put it into the first law of thermodynamics. So we're going to use negative P delta V inside our equation for the first law of thermodynamics. So our equation becomes the change in energy equals negative work done by the gas plus the heat exchanged with the environment. All right, so let's do an example. A piston of gas is compressed and the pressure is constant. How much work is done on the gas during the process? So we have this graph. It tells us our final volume is 100 cubic centimeters. It tells us our initial volume is 300 cubic centimeters, and our pressure is constant, so this is an isobaric process. Since it's isobaric, we can use P delta V. But we do need to convert our units. So we're going to have to convert our initial volume from 100 cubic centimeters into cubic meters, and this is going to be our conversion. And we're going to convert our final volume into, this is our final volume, and this is our initial volume into cubic meters. So once we have it in cubic meters, we can put it into our equation. The work done by gas is P delta V. We have our pressure. It was given in kilopascal, so we need to do times 10 to the third. Put our numbers in, VF minus VI, and we get a work of negative 40 joules. Well, the question is how much work is done on the gas, and this equation gives us how much work is done by the gas. So we're going to need to multiply it by -1 because W is negative the work done by the gas, and that gives us that 40 joules of work is done on the gas. The next thing we're going to talk about is an adiabatic process, and this is any time a thermodynamic process in which heat is not exchanged with the environment. That means that in our equation delta E is Q plus W, that Q is equal to 0. So there's no heat exchange. Either the process happens very quickly or it's well insulated, so there's no heat exchange. This is a diagram that shows a PV diagram that shows an adiabatic process of adiabatic expansion. And expansion means the volume is increasing. So we start at this volume, we go to this volume. Our heat is not lost or gained from the environment. And so you see that this is what's going to happen. As an expanding gas does work, an expanding gas is going to do work because it's going to press on expand a piston or expand the system. So the work done is going to be greater than 0. The first law of thermodynamics, we can use this equation. Remember that W gas has to be negative in this equation. W gas is greater than 0. Adiabatic says Q is equal to 0. So this is negative, a number that's greater than 0, plus a 0. That means that the sum of these two is going to be a negative number. That means that the change in thermal energy is less than 0. Temperature is related to thermal energy, and so the conclusion is, and this is an important idea about adiabatic expansion, as something is expanding adiabatically, the temperature of the gas is going to be lowering. The opposite, when we have adiabatic compression, that means the gas is getting in a smaller volume. Since the volume is getting smaller, the work done by the gas is going to be negative. By the first law of thermodynamics, we can take this equation. Remember, this work done by gas is negative, and in this equation we multiply it by -1, so that's going to end up being positive. And Q is 0. That means that these two numbers added together, the change in thermal energy is going to be a positive value. Since the temperature is proportional to the change in thermal energy, that means that an adiabatic compression raises the temperature of the gas.